Hello, class. So this will be a recorded lecture for section 3.4, and this will be the last of the recorded lectures before our first exam. And this is introducing inverse trig function using the right triangle approach and the practicality of using the inverse trig functions to do some calculations. And so let's go to the slides here and show you a couple definitions. So when we look at this graph, this is really good. This is slide 5 that's uploaded to our Brightspace account, and it's really good to show the definition of the three inverse trig functions. And remember, when we use the right triangle approach, the sine of theta is opposite over adjacent, or opposite over hypotenuse. And so that's the y value divided by r. Cosine is the adjacent over hypotenuse, so that would be x over r. And remember, tangent is opposite over adjacent, and that's x. It should be y over x, that is backwards, sorry about that. Y over x. And remember that it's only defined in two specific quadrants for the angles. In sine and tangent, it's from 90 to minus 90, and cosine is from 0 to 180. So again, defined for sine in quadrant 1 and 4, tangent quadrant 1 and 4, and cosine quadrants 1 and 2. So what do we do when we're actually doing some calculations? Well, let me just show you an example. So here's an example where we could use the inverse trig function to calculate an angle given two sides now, especially if it's a right triangle approach. And you can do that in a non-right triangle approach using the laws of sines and cosines, which we will do later on in the semester. But now we're just going to focus on using inverse trig functions to calculate some angles given two sides in a right triangle. So let's start with this example. So here we have theta, right? And here we're given, this is 50. Here's our right angle here. And this is 10. And the question is, what is theta? What is the angle? Well, you know, in a right triangle that all three angles add up to 180. And so this has to be a positive angle, and it looks like it's going to have to be in quadrant 1, right? And so if we think about this, we have theta, and this is the hypotenuse, right? And what is this side? This is the opposite side, right? So what is opposite over hypotenuse? That's our sine function. So to do this calculation, what we have is sine of theta equals opposite, which is 10, and hypotenuse, which is 50. So how do we get rid of sine and get our theta back? Well, what we want to do is take the inverse of both sides, just like we were doing before, right? And so these cancel, and we have theta over here, and then we have sine inverse of 10 over 50. So what is that answer? Well, you would have to get your calculator out now, and you would do 10 and divide it by 50, and then you would take the inverse sine. And when you do that, I have mine set to degrees, and you have about 11.5 degrees. And then the good news is when you use your calculator to do these calculations, the interval of angles that are appropriate are built into your calculator. So you'll always get the correct answer with regard to that. And one thing that I do want to point out that I think I skipped that slide. And so just to go back, but I was wanted to show you a practical reason for inverses, and there it is we have these ideas of domains and range, and the domain is the input to the function. And remember, if you look at the sine and cosine graphs, right, they never go above 1 or below -1. So that's the only input to the inverse, where remember tangent, any number works. So all real numbers can go into the inverse tangent function. So let's do another one. So say like we have this here. And so go into the whiteboard. I give you this here. And we know what this is already, but the numbers are kind of nice. So, and we have it set up where there's the right angle, and here is theta. So what is theta? Well, this is a 3, 4, 5 right triangle, right? So you could do this in a variety of different ways, right? So say like you wanted to use sine. Well, remember sine is opposite over hypotenuse, right? And this side is opposite, and this side is the hypotenuse, which makes this side adjacent, right? Because it's adjacent to the angle. So when you set this one up, sine of theta would equal opposite, which is 3, and hypotenuse, which is 5. And then you take the sine inverse of both sides. You would see theta equals, and if you did that calculation, it'd be 3, 5 divide, and then you would get sorry for the pause there. I was typing something wrong in my calculator, so I hit pause. But back, if you did that, you would see you would get 36.9 degrees. So there's, you could use any trig function though, if you think about it, because we have all 3 sides, right? So say like we wanted to use cosine. So cosine of theta would be adjacent over hypotenuse, right? So that would be 4 over 5. And then when you take the cosine inverse of both sides, these cosides cancel. And when you do this and you punch that 4 over 5 into your calculator, you would also get 36.9 degrees. And the same thing with tangent. Say like you wanted to use tangent. Well, tangent in this case is opposite over adjacent. So that would be 3 over 4. And then if you take tan inverse of both sides, right? Those would cancel, and theta equals, so what would that be, 0.75 arctan. And again, you get the exact same answer, 36.9 degrees. So one of the things with regards to strategy is if you're only given 2 sides, you have to make sure what is the correct trig function, trig inverse function to use to do the calculation. The only 3 that you will use is sine, cosine, and tangent. The other 3 are pretty much unusable, but don't repeat that. And so let's do one more example. And so here's kind of a fun little semi-real world application where you have this ladder. And the ladder is 40 feet. And we have the ladder 6 feet away from the building. And the question is, what is the angle that the ladder makes between the top of the ladder and where it hits the building there on the top? And so to do this calculation, we definitely are going to use the inverse. So let me pick brown because we have a building here, right? So there's our building. And then if the ladder's in red, the ladder's sticking right here. And this angle here is theta. This distance here is 6 feet. And the distance of the ladder is 40 feet, excuse me, 40 feet. And the question is, what is theta? Well, first thing you want to do is to figure out where the right angle is, right? So the right angle actually is from the ground to the building. So where's the hypotenuse? So the hypotenuse is always directly across the right angle. So this would be the hypotenuse, right? And so the building is actually adjacent because it's connected to that angle, right? And this would be opposite. So the two sides that we are given is the hypotenuse, which is 40 feet, and the opposite, which is 6 feet. So what do you think is the right trig function to use? Sine, right? Because remember, sine is opposite over hypotenuse. So when you set this up, we know that sine of our angle is going to equal 6 divided by 40. So then when you take the inverse of both sides, cancel out, and theta would be sine inverse of 6 over 40. So how do you get that? Well, you got to get your calculator back up. So it'd be 6 divided by 40, and that's 0.15. And then when you take the inverse sine of that, you get approximately 8.6 degrees. So this is the practical applications of using inverse trig functions. And as an electrical engineer, I didn't use them that much. I used the other part of the trig world a lot more. But if you were in mechanical architecture, things like that, and you want to know what angles are given certain sides of triangles, very, very, very useful. And so this is the practical applications of inverse trig functions. So that ends section 3.4. Actually, section 2.6 and 3.4 are combined as an inverse trig functions for definition and then for practicality use using the right triangle.